Yeah. Good afternoon or good evening to all of you. And let me welcome all of you for this live session for the course on Cathodic Protection Engineering. Now, first of all, let me thank all of you for enrolling this particular course. I do hope that you found this course is useful to understand the basics of Cathodic protection. The course is mainly given emphasis on the basic aspects of it. Of course, you also have some problems to solve. I'm also happy that this course is well received. We have more than 700 or close to 800 people have enrolled for this particular course. So let me hear from you if you have any questions so that we can discuss. Okay. Is it possible for the participant to unmute and ask questions directly, or they can do only chatting through the chat box? Only chat box, is it? Okay. Yeah, this is a little unfortunate. So let me start reading some information that has come in the chat box. Satish Kumar B. The question is, please explain assignment number 1, the last question, right? So let me first of all read this assignment 1, the last question itself. The question reads as follows. For the above problem, determine the current required to be passed to bring down the above corrosion rate. If the cathodic tapered slope is 120 millivolt per decade, okay? Now, to what extent you bring down the corrosion rate is given by the corrosion current density here, okay? One is 1.9369 milliampere per centimeter square, and so on, right? 0.07446 milliampere per centimeter square. Other is 1.5199 milliampere per centimeter square, and again 0.34164 milliampere per centimeter square. So you need to bring down the potential. You are bringing down the potential to what? To minus 0.85, isn't it? Minus 0.85 is the voltage that you need to bring down. Now, this problem is also clubbed with the previous problem. Okay, let's look at the previous problem. The previous problem is 7, right? Problem 7 reads, a steel tank has been found showing a natural potential, which is corrosion potential, of minus 750 millivolts with respect to copper, saturated copper sulfate reference electrode. The metal was found to, to corrode at 200 mpy. What should be the potential of the steel tank with respect to copper sulfate reference electrode to reduce its corrosion rate to 10 mpy? Given the anodic tapered slope of 60 millivolt per decade for steel, the atomic mass unit is 55.85 grams. Density is 7.88 gram per centimeter centimeter cube. Okay. So, of course, I have also given here a reference to the lecture on 10. We give the numericals. Now, you see, now we have given the corrosion rate, right? I suppose you saw the problem 7. You have given the corrosion rate is in terms of MPY. Now we are asking the potentials. So there is a relation between the potential and the corrosion rate via the current density, right? So that means the corrosion rate in terms of MPY must be converted into current density, right? When you convert to current density, so that is the rate at which the metal is corroding. At that corrosion rate, ICAR value, it exhibits a potential of minus 750 millivolts, right? That is the potential that the buried metal in the soil exhibits the potentials. So you know the ICAR value, you know the ECAR value, okay? Now you need to bring down the corrosion rate from 200 MPY to 10 MPY. So you can also find out what is the corresponding current density for 10 MPY, isn't it? You can go through same Faraday laws and find out what is the equivalent of the ICAR value corresponding to 10, approximately about 10 times, about how many times it's going to be? About 20 times, right? So you can able to calculate it. So I know that at the ECAR, what is ICAR? Okay. Now what you are doing is you are reducing that current ICAR to another value which is equal to 10 MPY, which is some ICAR value. Now, since the tablet slopes are given to you, okay, is 60 millivolt. So what you can do, you can use the tablet equation, eta, isn't it? You guys know the tablet equation. Let me now show this. This one, right? This one?
Yes.
Okay. Okay. So let me recall, you must be knowing this equation, eta is equal to, eta is equal to plus beta log I by I naught, okay? Or you can put as, or you can say plus or eta is equal to beta log I by I card. You can put any of these things like that, actually, right? Okay, then what is eta in this case? The eta in this case is equal to E corresponding to the applied value minus E card, right? So now you have the value of I by I car. I car, what talk about this corresponds to this particular potentials now, right? Now this is about the value that you're looking at corresponding to 10 MPY. This corresponds to 200 MPY, right? Isn't it? So you know this value, this is equal to what? It's equal to 60 milliwatt per decade, right? Isn't it? Right? So you can calculate what should be the E applied. So that is what is asked in the previous question. Now the next question is very similar. What has happened here is, instead of giving the anodic tapered slope, what is given now is a cathodic tapered slope, right? The cathodic tapered slope here is, say again, in this case, eta is equal to minus beta, this cathodic slope, logarithm of I upon I naught, or I car, you can say, whatever you can call it, right? So you know this value, again here. The only difference here is the tapered slope. Tapered slope is 120 millivolts, right, per decade. So you substitute this one, you should be able to get what is the applied potentials. Okay. So the idea here is, it is possible for you to obtain the E applied value. Either you have a anodic tapered slope or a cathodic tapered slope. It's both ways it's possible for you to obtain this. So that is the whole idea of giving this particular problem. I hope you were able to get it right. And if you have any questions, you please again send your question on the chat box. Are there any other questions? Yeah, can you please tell me?
Dr. Dawal Kumar Sharma asks, consumable anodes can be used in ICCP also, true or not?
Yeah. Well, I think, okay. So, this is Dr.
Dr. Dawal Kumar Sharma.
Yeah, Dr. Sharma, thanks for the very nice question. I just wanted to clarify that we have two types of anodes that we need to understand. One is called as sacrificial anodes. Other is called as the impressed current anodes. The sacrificial anodes are used to protect the structures. The sacrificial anodes dissolve and then they deliver the current to the structures. So the current is now derived from the dissolution of the sacrificial anode. Okay. Now, what else the sacrificial anode do? The sacrificial anodes also provide the driving force for the current to be delivered from the anode to the structures. So the sacrificial anodes have two functions. They deliver the current. They also give the driving voltage so that the current will go to the protector structures. In that case, these anodes that dissolve. Now, let's look at the impressed current anodes. The impressed current anodes are employed primarily to pass the current in the soil. The current will enter the soil and then they'll travel and they enter the structures. The driving force is given by the rectifier. The current is also given by the rectifier. Okay. Now, please notice in the impressed current, the purpose of the anodes is to just deliver the current, that is, pass the current. It's only a conductor. Now, coming to your question, can the impressed current anodes be consumable anodes? Yeah, it can be consumable anodes. For example, you can have steel scraps. Okay. You can even have a steel anode, for example. But then the dissolution occurs because it is made as an anode and the anode dissolves when the current is passed. Because whenever you make steel as an anode, it dissolves. But please don't mistake that dissolution is happening as a consequence of passing current onto the anode. And that current is not counted in protecting the steel structures. Okay. So they are called consumable anodes because they get consumed during passage of the current. Now we have a dimensionally stable anode, right? Like a titanium insoluble anode, for example. You pass the current. Now there the anodes are very stable. Of course, there will be small amount of dissolution in terms of micrograms. But you don't call them as consumable anodes because the amount of damage or dissolution that occurs due to the passage of current is very small. Okay. So coming back to your point, yes, the consumable anodes can be the impressed current cathodic protection anodes. But that consumption is not related to the current that is available for protecting the structures, nor the potential so delivered is sufficient to protect the structures without applying cathodic protection externally, right? So this is something very, very important. Okay, so we need to understand the difference between a sacrificial anode and a consumable anode in a proper context. I hope you get the answers. If you still have questions, please do let me know. So any other questions? Okay, if there are no questions, can we close the discussion, live session? So I'll give you another minute or so. You please think over. If any of you have any questions, please put them in the chat box. Okay, so thank you, gentlemen, for attending the live session and asking very useful and nice questions. Thank you very much. And we'll now close the live session. Thank you.